All right, finally, they're working. In a solution, the particles, the solute particles, are so small that they don't scatter light. This is solute. And then light just goes through. And so these are transparent. In other words, they're clear. They could have color, though, but they're clear to light. And so they could be clear colorless, or clear yellow, or clear blue. They don't scatter light. Then we have colloidal solutions. Colloidal solutions. In colloidal solutions, the particles are a bit bigger. Since we have bigger particles, they're bigger particles, however, they're still small enough that they're permanently suspended. That is, they don't sink to the bottom. And so these are permanently suspended, or suspended. And so what happens with a colloidal solution is they scatter light, because the solute particles are getting a bit bigger, and so they can interact with visible light. And because they scatter light, they are not clear. You know, they're either translucent or opaque. You know. And so that's how, one of the ways you can tell. You can hold a flashlight, and if you hold a flashlight, there's a glow to this, whereas a flashlight would just go straight through. And so this is actually at the end of chapter 14, but we'll talk about it now. So let's take a look at colloidal solutions and Tyndall effect. Here you can see the solution, the light just goes straight through it, it's clear. However, when we look at the colloidal solution, we see a glow to that. That's the Tyndall effect here. If you can get the particles bigger, then what we form is a suspension. A suspension would be what you guys were trying to form by coagulating the colloidal particles. You coagulate them to form bigger crystals, and eventually they're going to sink to the bottom, precipitate. And so the suspension might be temporarily suspended, but eventually it'll sink and settle to the bottom of the test tube. And so an example of this would be like muddy water, you know, where the mud might be temporarily suspended, but it's not going to stay suspended forever, because the particles of mud are too big, and gravity is going to take over and it'll settle. And so these are based on solute size. The solution, very small; colloidal, medium; suspension, large. So you guys learned about colloidal particles, surface charge, this kind of stuff. For the lab. So let's take a look at some of the terminology. Solvent, solute. Solute's the minor component. Alloys are typically examples of solid solutions. So for example, the nickel is not pure nickel. The nickel is made up of 75% copper, 25% nickel, and that's just on the surface. Inside they probably use zinc, which is a lot cheaper. There are different kinds of alloys depending on, you know, where the atoms fit. It depends on the size of the metals. So for example, if you mix two metals that have similar sized atoms, then the other atom can just substitute for the position. And so we could have something like this. I think they call this substitutional alloy. And so these will mix in any proportion here. So have that. So this would be one type of alloy. In another type of alloy, the other atoms are kind of small. If the other atoms are kind of small, then they can fit where? In between the atoms, right? And so it depends on how many holes. We got lots of holes here. And so you can have almost any ratio here as well. These are mixtures because they can be in any proportion. They don't have to be in a fixed ratio. And so this is called a substitutional alloy. This is called an interstitial alloy, where it fits in the little interstices of it. Other terms here depend on, solute, solvent, solubility. Solubility has two definitions. There's the qualitative definition. Most of the time, for the qualitative definition, the limit is set at 0.1 molar. But it depends on who's defining it. And so for qualitative, if the solubility is greater, S has different definitions as well, so I'll just call it the solubility. If the solubility is greater than 0.1 molar, then we call it soluble. If the solubility is less than 0.1 molar, then it's insoluble. And so we use this S to refer to soluble versus solubility, and I refers to insoluble here. If the solubility is around 0.1 molar, then we call it slightly soluble. Slightly soluble gets the abbreviation SS. And so these are qualitative. Qualitatively, we go SISS. Soluble, insoluble, slightly soluble. And the limits are around 0.1 molar. Well, 0.1 molar, that's still fairly concentrated. So if you get like 0.09 molar, then we're going to call it insoluble, but it really probably we should call it slightly soluble. Okay, the other definition of solubility is quantitative. The quantitative is just the max amount of solute for a given amount of solvent or solution. So it depends on the units. We just take a look at the units. And a lot of these are grams per 100 milliliters. And so typical units would be in grams of solute per 100 milliliters of solvent, like water. And so this is pretty easy to measure, because you just take 100 milliliters of water and then add how many grams, the maximum number of grams that will dissolve in it, and just figure it out. Some things have fairly high, but then to relate it to this, the molar solubility, or we could have the molar solubility, which would be moles of solute per liter of solution. the maximum number of moles that we can dissolve in a liter of that solution, etc. So that would be the quantitative. But there are lots of different units that you see for solubility. You know, grams per 100 milliliters, molar, the molar solubility. There are a bunch of others. And so what are all the other units for solubility, this etc.? And so solution composition. These are two examples here, but some others are mass percent, mass to volume percent. And so we have percent composition. There are different percentages. There's the percent m over m, which would just be a mass percent. This would be mass of solute over mass of solution. This would be total mass. In other words, the solution mass. Solution is the total. And that's just equal to the mass of solute divided by the mass of solution times 100%. Then we'll have all the variations of percent. Percent is part per 100. Part per 100. And then we'll have things like, another common one is if the percent gets very small, it becomes inconvenient. So let's say you're dealing with 0.00001%. This is not a very convenient unit. It's like if you're dealing with 0.00001 grams, you probably want to use like milligrams or micrograms. Be a lot more convenient. And so for ppm, it's basically just the same. Basically m over m, except we times it by 1,000,000 ppm rather than a percent. So this is going to make the number a lot bigger. And so rather than dealing with 0.00001%, we're going to have something more convenient. And then we have part per billion. It's the same thing except we multiply by billion ppb, or part per trillion, which is multiplied by a trillion part ppt. And then of course we can reverse it. The reverse is, let's say we have a percentage and we want to get the fraction or the decimal. And so if we want to go fractional or decimal, then we just multiply it or divide it. What do we do? We divide it by 100%. And so if it's 6%, then that's 6 out of 100. And if it's mass, we'll just go grams over 100 grams. Let's say if I had 1 ppm, then that's 1 gram over 1,000,000 grams. This is solute. This is solution. We have to be careful because is it solution or solvent? Sometimes it's solvent, like in this case. This is solute over solvent here. And so these are easy to reverse. If I had 3 ppb, then the conversion factor I'd get from that is 3 grams of solute per billion grams of solution, etc. All right, the volume percent is pretty much the same, except if I'm dealing with a volume percent, I have to make sure, the conversion is going to be different. This is grams per grams, And so if I had something like, let's say 6%, and this is a V over V, percentage, then that's going to be 6, milliliters or whatever unit you want per 100 milliliters. So 6 milliliters of solute per 100 milliliters of solution, etc. So it's the same exact thing, except the units are different. But I could have a M over V. And so if I do this, this is 0.9% M over V sodium chloride. It has a common use. Do you know what it is? Yeah. Let's see. It's actually called
density. Density. Grams per mil.
Because it's grams of molding per liter of something else.
Yeah. So you can use it for density. It's one could be milliliters of milliliters. So you can use grams of milliliters for 1% density.
So 0.9% sodium chloride or 0.9% NaCl are often called normal saline. Normal saline, this is a saline solution that we call isotonic saline. Isotonic saline has the same concentration as blood. So if you get an IV of saline solution, it's 0.9% M over V NaCl. And so how do I write that as a fraction? 0.9 over 100. That's correct. Okay, 0.9 what? Grams of NaCl per 100 milliliters of solution. That would be it. So they're talking, it's important because for intravenous fluids, it is common practice to give intravenous fluids to patients with serious acute infections, but there is no agreement as to what the sodium concentration of these fluids should be. Doctors have traditionally used intravenous fluid that contains a lower sodium concentration than is found normally in human serum. This is known as hypotonic saline. However, as patients with severe infections often have low sodium levels and adverse effects sometimes occur with the use of large amounts of hypotonic saline, it has been proposed to use intravenous fluids that have a sodium concentration similar to that of a healthy person, isotonic saline. This review has been unable to find any data from randomized trials that establish which is best. Okay, so that's often the case, more studies are necessary.
What is a human serum? Is it
Blood.
referring to blood?
Blood, yes. When was this published? This was published in 2003, so it's a bit old. Maybe they have some more recent data.
I feel like there should be a lot of research on this.
Yeah, I'm sure there's plenty of research on this. But these are things you find. I mean, is it really going to make a huge difference? The saline solutions they're using are not that much different. 0.3, they're using 0.3 to 0.3, or no, 1.18 to 0.3 for hypotonic. So there is something there. And so sometimes we see M over V. More convenient for certain things. And so we have the parts per million, the parts per billion, and the parts per trillion. These are very common units. They're common units for like impurities. Let's see, because these terms are widely used in environmental reporting, they may be more familiar than other units that chemists use. For example, a consumer in California might read in an annual water quality report from the municipal water department that the maximum contaminant level allowed for nitrate ion is 45 ppm, and for carbon tetrachloride is 0.5 ppb. parts per billion. So yeah, I usually read the water quality to see what kind of contaminants are in the water. However, this is another weird thing. In the water quality, they might use milligrams per liter. A milligram per liter is also a part per million. How many milligrams are there in a liter? Well, a liter is going to have 1,000 grams. 1,000 grams is going to be 1,000,000 milligrams. And so this is 1 milligram per million milligrams. 1 milligram of what per milligram? This is going to be 1 milligram of solute per million milligrams of solution. And so this is when somebody sees a milligram per liter, that's a part per million. And so oftentimes when you look at the water quality reports, it's written, rather than in ppm, milligrams per liter. Or parts per billion is often written micrograms per liter, or parts per million is a microgram per milliliter. And so you have all these other units for ppm that you have to be aware of. Milligram per liter, microgram per milliliter. All say the same thing, and so you just recognize that. Parts per billion is microgram per liter. Or in terms of milliliters, it would be nanogram per milliliter. Depends. Some people prefer per liter, some people prefer per milliliter. And you have to recognize all those, as being equivalent. But, the part per million is so common that either milligram per liter or microgram per milliliter, same thing. Uh-huh.
I looked it up, right? In a 2019 study, there's apparently 5,300 ppb lead in water in Illinois.
In Illinois, wow.
Yeah.
Wow. 5,300 ppb,
Yes.
which would be 5,300 ppb would be 5.3 ppm.
Yes.
5.3 ppm, yeah, that seems high.
Yes.
But so like Detroit and some of those old cities, they have all that lead piping still that they haven't replaced, and so the lead levels are quite high. Lead was used for a lot of plumbing one time. What's that? Yeah, back in the day, but all that lead plumbing hasn't been changed. It's still lead plumbing. They should, if they want to spend money and improve people's health, then they should change that. I don't know what they're spending money on right now, but that would be a good project to spend money on.
Switch over from lead to copper.
Yeah, switch it from lead to copper, or switch it, and just get rid of the lead. And get the lead out, as they say. All right, so that's a M over B. We also have percent mole. When we have percent mole, that means it's either in terms of molecules or moles of molecules. And so mole percent is very common. A mole percent is going to be the moles of solute over the total moles. This first part is called the mole fraction. And it's actually given a symbol. The mole fraction is chi, the Greek letter chi. And this is going to be chi of the solute. And then we times it by 100%. And so we'll take a look at the mole fraction and the mole percent here. So here's the mole fraction, chi. And it's just the amount of component I in moles divided by the total moles. All the mole fractions have to add up to 1. All the mole percentages have to add up to 100%. And so if either you represent it in fractional form, 50 out of 100. 50 out of 100, that's 50%. 50 out of 100 would be 1/2. That would be the mole fraction 1/2. So why do we care about mole fractions? We use mole fractions for different things. So later on, we use mole fractions in something called colligative properties. And we'll talk about colligative properties briefly. so just like mole fraction, this would be the mass fraction. If we take the mass fraction, multiply by 100%, we get the mass percent. If we take the volume fraction, multiply by 100%, we get the percent by volume. So there's nothing special about the mole fraction, except we're going to use it in future equations, so therefore we need a symbol for it. Everybody knows molarity, right? Everybody knows molarity. I'm going to skip molarity. Molarity is the most common. What's nice about molarity is it's great for stoichiometry. You do solution stoichiometry, you can go direct from liters of solution to moles of solute. The bad thing, there's one bad thing about molarity. Do you know what the bad thing about molarity is? The one bad thing about molarity is it depends on temperature. Because what happens is the molarity changes with temperature. So if it gets hot and the liquid expands, things expand when they get hot, then the molarity just went down. If it gets cold and the liquid contracts, then the molarity just went up. And so molarity changes with temperature. And therefore, if you're doing things with fluctuating temperature, it'll drive you crazy. Because you got to recalculate the molarity for each temperature. Do you want to do that? No, that's a nightmare. So fortunately, we always work at 25 degrees C, or try to, right? But it's not always the case. This lab is not controlled. The temperature is not 25 degrees C in this lab. I don't know if there's been one day that the temperature has been 25 degrees C. Yeah, it's usually a lot colder. But anyway, so we have other concentration units. Does mass percent depend on temperature? No. How about volume percent? Does volume percent depend on temperature?
Yes.
Potentially, yes. And mass over volume percent would depend on temperature. Okay, there's another unit that does not depend on temperature, and that is molality. The molality is a lot less convenient. But when we're doing things that, where the temperature changes a lot, then we don't want to use molarity, we want to use molality. And molality is defined as moles of solute per kilogram of solvent. This is not solution, it's just the solvent. And so the mass of the solute and the mass of the solvent is not going to change with temperature. And so it's a bit more of a pain to deal with molality. Let's take a look at this example here. An ethanol water solution is prepared by dissolving 10 milliliters of ethanol, and they give us the density here. And so from 10 milliliters, we can figure out precisely how many grams, the 3 sig figs. We have 4 sig figs here for the ethanol. In a sufficient volume of water to produce 100 milliliters of solution with a density of 0.982 milliliters, or not, grams per milliliter, excuse me. What is the concentration of ethanol in this solution expressed as A, a volume percent, B, a mass percent, C, a mass to volume percent, D, a mole fraction, E, a mole percent, F, a molarity, G, a molality. Wow, this hits all of them. If you could do this one, then you're good. It's more than adequate. And so, well, as far as volume percent, it's easy. 10 milliliters of ethanol, 100 milliliters solution, times 100%, 10.00%, 4 sig figs there. Mass percent of ethanol, so we got to figure out how many grams of ethanol over the total grams. And so the grams of ethanol is just the milliliters times the density, known to 3 sig figs. And then they give us the density of the final solution. So we know we have 100 milliliters of final solution, and they give us the density of that, and we get the grams. So the grams of solute over grams of solution, the solution is total times 100%, 8.03%. Mass to volume percent, and so just grams of ethanol over 100 milliliters solution times 100%, 7.89%. Let's take a look at the rest of these quickly. Mole fraction. So we have to calculate, we need to know how many moles. So we start off with grams and convert to moles. With grams of pure ethanol, not grams of solution here. We got that many moles of solute. Then we got to figure out how many moles of solution we have. And so if we have 7.89 grams of ethanol and 100 grams of solution, then we're going to have, or 98.2 grams of solution, we're going to have 100 milliliters. 100 milliliters is 98.2 grams. We're going to have 90.3 grams of water. And so here we can convert grams of ethanol to moles of ethanol and grams of water into moles of water. And so that's going to give us the total moles. So this is moles of solute over the total moles. That's the mole fraction. The mole fraction is 0.171 over 5.18. And then we divide that, we get 0.0330 over 1. That would be the mole fraction. So we could have the mole fraction. Usually mole fraction is expressed in decimal form. And that's called chi. So this would be chi ethanol. And then what do we do with the mole fraction? We use that for other calculations later on in the chapter. The mole percent is just take the mole fraction times 100%, 3.30%. The molarity of ethanol is moles of ethanol over liters of solution, so 1.71 molar. And finally, the molality. So first we have to figure out how many kilograms of water. So it's 90.3 grams, so 0.093903 kilograms of water. And then we take the moles of ethanol divided by the kilograms of solvent. The solvent consists of the solute plus the, the solvent. Yeah, the solvent just consists of the solvent, but the solution consists of the solute plus the solvent. So we just have to be careful with that. And so those are the most common composition units that we use. All right, the next thing we're going to look at is the energetics of solution formation. We break in this is dissolution or solution formation. We break it up into 3 steps for the energetics of this. Step 1, obviously these steps are going to happen simultaneously, pretty much. And but for thermo, we break it up into 3 steps. This is for thermodynamics. So step 1 is we need to break the solute attractions. So we have to break apart the solute particles. This is going to be endothermic. It's going to cost us energy. And so we got to either break the IMFs, which could be London, dipole, hydrogen bonding, or we got to break actual bonds like ionic bonds. Like if we want to dissolve sodium chloride, then this would be delta H of the lattice, essentially. And so that's endothermic. Step 2, do 3 steps, is we're going to form. Or actually not form. We're going to have to break. What else do we have to break? I got these backwards. That doesn't matter. We have to break the solvent attraction. So in other words, we got to break the solute particles apart. We got to break the solvent. Why do we have to break the solvent? We have to make room for the solute to fit in there. So we'll call this delta H2. That's going to be endothermic also. And so here's delta H1. Here's delta H2. Both of these are endothermic. Okay, step 3 will be exothermic. Whenever we break apart things, it's going to cost us energy. But when we form bonds or form intermolecular forces, then that's going to release energy. So we're going to form solute, solvent attractions. You know, whatever's holding them together. I call them attractions because it could be IMFs or bonds. This is going to be exothermic, so delta H3 should be less than 0. Here's an energy level diagram. This energy level diagram is called an enthalpy diagram. We're going to have enthalpy here, so we're going to just do this under constant pressure conditions. If we do this under constant pressure conditions, then we might as well just use enthalpy because in case there's a volume change. And so the enthalpy goes up. In other words, the energy goes up. Ideally, this would be exothermic. So, here. If it's exothermic, it should be downhill overall. You know. And so here's our starting. And we have delta H of solution. Delta H of solution is you add these up by Hess's law. And delta H of solution's here. This is the dissolution process. And it's great if it's exothermic. Or 0. If there's no change in energy, should it happen? What's the driving force? If there's no change in energy, should it happen? And the answer is yes, it should happen. What if it's positive? Should it happen? And so this is what we're going to end up with here. Solution formation is favorable if delta H is less than 0, for sure. Or delta H is equal to 0. Or delta H is just slightly greater than 0. It's unfavorable if delta H is much greater than 0. So we'll just say slightly. But this is different than, you know, when we're talking about uphill because of the Maxwell-Boltzmann distribution, some can make it uphill, right? There's going to be a small population that makes it uphill. But this is a little bit different. In this case, if we have a slight uphill, a lot can make it uphill. So for example, sodium chloride. Is sodium chloride soluble? But did you know sodium chloride has a delta H of solution that's greater than 0? And so here, the example would be sodium chloride. Sodium chloride is highly soluble. Its solubility is like, what is it, 7? Yeah, something like that, 7 grams per 100 milliliters, 6. Anyway, but it's slightly endothermic. And that is, there are different ways of thinking about this. About one of the things we think about, what does nature like to do? Nature likes to minimize energy. And so let's look at driving forces. There are different ways of thinking about driving forces. One, we want to minimize energy. So when we think about gravitational potential energy, we want to minimize that. And so this is at high gravitational potential energy, and the driving force is it's going to go to low gravitational potential energy. Would it go from high gravitational potential energy to even higher gravitational potential energy? No, because nature wants to minimize that. However, this solution is doing that. This is going from lower energy to higher energy. How is that possible? It would be like the pen going up. And how it's possible is this. In physics, you're usually just working with one object. In chemistry, you're working with moles of object. And when you have moles of object, there's one more thing that we have to worry about, and that's something called entropy. And so we want to maximize entropy. And so what happens in nature is we minimize energy, maximize entropy. And so what is entropy? Entropy is a measure of disorder. The higher the entropy, the more disordered. And so it's like, this has happened to me when I was young, and it still happens to me. I take something apart. I take something apart to see how it works, but I couldn't put it back together. And so it was easy to take apart, but it was hard to get it back together so that it worked again. Has that happened to you? And so it's very easy to destroy things, but it's very hard to build things. So if we want to destroy a building, no problem. But to build that building, boy, that's tough. And so, yeah, this happens, this destruction is easy. But building things is not so easy. And so this is what we mean by maximizing entropy. It's easy to make a mess. It's hard to keep things clean, for me. But all of these are related to entropy. Actually, minimizing energy is also related to entropy as well, because we have different kinds of energy. We have higher entropy energy, higher disorder in energy. And the highest disorder in energy is the least useful. And then we have lower entropy energy. So for example, if you had, let's say, 100 kilojoules, you could have 100 kilojoules of kinetic energy, heat. Or you could have 100 kilojoules of potential chemical energy, that is hydrogen and oxygen ready to explode. Which one's more useful? 100 kilojoules of heat or 100 kilojoules of potential energy, like in a battery or in a chemical reaction?
100 kilojoules of heat, more readily usable.
More readily usable?
Kinetic energy.
Okay. Is it more readily usable to make things, to build buildings,
No.
to drive a electric nail gun or whatever they use?
It's much easier to stand around and do it.
Yeah, and so there's different entropies of energy too. It's called energy entropy. Heat is the least useful. Eventually, the energy. This is getting into the laws of thermodynamics. The laws of thermodynamics are talked about in Chem 1B in more detail. We already talked about the first law of thermodynamics. First law of thermodynamics is what? Somebody remind me what the first law of thermodynamics states? Energy is neither created nor destroyed. And so that means the energy content of the universe is fixed. We have a certain amount of energy and that's it. However, the entropy, what's happening with the entropy of the universe?
Flux.
The entropy of the universe is going up. Once it stops going up, then what do we have? Nothing, and there's no more driving force. Nature, it's a weird thing to think about, but then they would think everything would be evenly dispersed, heat, whatever, particles.
So, Professor,
Uh-huh.
the higher entropy is, the greater measure of disorder.
Yes.
Okay.
So we look at types of things we break and types of things we form. So this is benzene, this is toluene. And we have things called an ideal solution and non-ideal solutions. So let's say I mix water with water. That's ideal because what we break are water and water. What we form is water. And so that's ideal. Right? There's no change. This is close to ideal. Benzene and toluene is very close to ideal because what do we break? We break benzene. We break toluene. What do we form? We form benzene, toluene. But you see they're so similar structurally? And so the IMFs that we're breaking, these are going to be London forces, and we're going to form London forces. So that's what we call an ideal solution. Ideal solutions are miscible. Have you heard that term, miscible? You know what miscible stands for? Infinitely soluble. In other words, it's like mixing water with water. Is there a limit to how much water you can mix with water? No, there's no limit. It's infinitely soluble. Well, some things are infinitely soluble, like methanol. Did you know methanol and water are miscible? Is there a limit to how much methanol you can mix with water? No, there's no limit. Pretty soon you're going to have so much methanol, you better flip it. That is called methanol the solvent and water the solute, which is fine. You know, you could flip it. It turns out that even ethanol and water is miscible also. Because they're methanol and ethanol are water-like. However, you go to propanol. Do you think propanol is miscible in water? No. And eventually you get to butanol or pentanol. When we get to pentanol, then we call it immiscible. And immiscible means it's not at all soluble because pentanol is more hydrocarbon-like, more oil than water-like. And so they don't mix, yeah. And so we just look at how well they mix. This is not perfectly ideal. This would be acetone in chloroform. You know, this has got the dipole-dipole interaction. You can see the dipole-dipole interaction here, but it's not. This is not ideal. So there's going to be a limit to how much you can mix. But, you know, there's going to be some, is this hydrogen bonding? They're calling it, what are they calling it? Hydrogen bonding between chloroform and acetone. This is not hydrogen bonding. Why are they calling this hydrogen bonding? It's not hydrogen bonding. What do you need for hydrogen bonding? You need hydrogen bonded to what atoms? What three atoms? Oxygen, fluorine, and nitrogen. And what that does is it makes an unusually large dipole because the hydrogen becomes partially de-shielded. Remember we talked about a partially exposed proton. Is carbon going to make this hydrogen partially de-shielded?
No.
Not at all. This is not hydrogen bonding. This is dipole-dipole. And so why do they call it hydrogen bonding? I don't know. That's a mistake. And so we should strike that. This is dipole-dipole.
So it's only hydrogen bonding if the hydrogen is bonded to either fluorine, oxygen, or nitrogen.
Yeah, and that's very favorable. So let's try to stick a benzene in water. Benzene and water will have favorable attractions because we're going to have dipole of water inducing a dipole in benzene. So it would be a dipole-induced dipole. It wouldn't be hydrogen bonding. It'd just be dipole-induced dipole, and water has a great big dipole, so it's good. The problem with dissolving benzene in water is you'd have to break too many waters apart, and water likes water. And if you have to break too many waters apart, it's going to cost you too much energy. And therefore, this is not going to form. That is, benzene in water. Well, maybe a tiny bit will dissolve, you know. This is, tiny bit will dissolve. And it's not, you know, and that goes with anything that's insoluble, you know, typically a tiny bit does dissolve. How do you spell Perrier? Water.
E-R-R-E-I-E-R.
I-E-R?
Perrier water vodka is the first thing I said. That's an interesting combination.
So you might have heard about this in early 1990 during some routine quality checks. The North Carolina health officials examined a few Perrier bottles and discovered elevated levels of benzene, a naturally occurring liquid that nonetheless, all things being equal, one would prefer not to sip over lunch. It's from Forbes. So how did the benzene get in there? Obviously the benzene is going to be hopefully at the part per million or the part per billion level. I don't know what the acceptable level of benzene is in drinking water. Anyway, Perrier Managing Director Frederick Zimmer said the contamination was caused when workers at the Perrier plant in Vergaz, I guess, in southern France failed to change a filter that is supposed to catch small amounts of benzene found naturally in the spring. Probably like a carbon filter, something like that. You know, like charcoal or carbon filter should extract the benzene.
I wouldn't be surprised if the acceptable range is something like 5 ppm.
No, I don't think it's that high.
The
Benzene,
acceptable
did you know
range.
benzene was banned for many years? I think benzene was banned for about 10 to 20 years. But benzene is one of those perfect solvents, you know, it's a very good solvent, and so it was banned because it was a suspected carcinogen, and then they eventually changed that because of course you want to be careful.
500 ppm.
Toluene's another common. These are two very common solvents in organic chemistry, benzene and toluene. Because of their shape, you know, I think the reasoning was benzene gets wedged in a groove of the DNA and then prevents or causes trouble from there, as I recall. So here's toluene. This is how organic chemists draw their structures. Organic chemists get very tired of writing C. And so all they do is they show the bonds. So this would be a carbon-carbon single bond, carbon-carbon double bond, carbon-hydrogen single bond. And so it's much faster if you don't have to draw the carbons. Every other atom, like oxygen, nitrogen, phosphorus, is drawn. The only ones that aren't are carbons, and the carbons occur at all the intersections here. And so it gives us a rapid way of writing Lewis structures. So here's this toluene, here's oxalic acid. Oxalic acid is going to have some great hydrogen bonding. You know, this is going to be London. This will be London and hydrogen bonding. Benzaldehyde, will this hydrogen bond? No. Benzaldehyde, this hydrogen's not bonded to the oxygen. This hydrogen's actually bonded to the carbon. But this is going to be more polar because this carbon's got this oxygen. There's going to be an inductive effect here. This inductive effect will make this hydrogen just very slightly acidic. Not a great. In fact, benzaldehyde's not really thought of as an acid. It's pretty weak. But this would probably be the most acidic hydrogen on these and susceptible to attack by base. Which one do you think is most readily soluble in water? Oxalic acid. Which one should be the most soluble in benzene? I would say toluene because this is more polar. I don't know. This could be good too. But in water, it's pretty obvious. And so that's the kind of question you get. Carbon disulfide is, carbon disulfide, I had to dissolve some wax. How do you dissolve wax?
Wax.
You could dissolve it in molten wax, yeah. So wax and wax would be miscible. But I didn't want, I had to dissolve it at room temperature. I couldn't heat it up. And so you know how I dissolved it? I used carbon disulfide. I was able to dissolve the wax in carbon disulfide at room temperature. Dissolving things isn't so easy. You know, dissolving things is a challenge. You guys got lucky with the sulfate, but in Chem 1B in the past, we used to give unknowns that didn't dissolve in water. You go, man, my unknown's not dissolving in water. What do I do next? Then you got to start thinking, you know, how are you going to get it to dissolve? Yeah, maybe alcohol. Try that. Normally the route goes like that. Water, hot water, then you give up on those, and then you go alcohol.
Hot alcohol.
Not hot alcohol because it's
I would definitely go that route.
alcohol, and then you go, maybe it's non-polar, like wax. And then you go hexane. Hexane's another solvent. Hexane is a great non-polar solvent. Or carbon disulfide. Carbon disulfide's a liquid, and it's another great solvent, but carbon disulfide stinks. So I didn't like it, working with it that much.
And then from there, just move on to acid.
Yeah, so this would be a dipole of acetone, inducing a dipole. Normally carbon disulfide is non-polar, but you can induce a dipole. So if this end goes here, that's negative, that's going to push the electrons to the other end and make this end positive. And so this would be dipole, permanent dipole, induced dipole. We don't call that London. London would be instantaneous dipole, induced dipole. Formation of ionic solutions. So here, if we dissolve salt, we have to break the ionic bonds, and then we have to break the hydrogen bonds holding water, and then we form these. These are called hydrated or solvated ions. And these hydrated or solvated ions are quite stable. And so these can easily make up. The lattice energy for this is high, you know, over 600 kilojoules per mole. 700 maybe. And so when we add this up, okay, first we got to break the lattice apart. That's the lattice energy. Then we got to break the solute. Well, this is a little different Hess's law. And so here's forming the hydrated sodium. Here's forming the hydrated chlorine. That's very favorable. And so we almost get that energy back. Breaking apart ionic bonds is going to cost a lot of energy. But forming these hydrated ions also releases a lot of energy, and we'll almost break even. It's just plus 5 kilojoules. At plus 5 kilojoules, will sodium chloride still dissolve? Yes. Why? Because of entropy. Entropy. Now, if it's too big, then it's not. So for example, if the lattice energy were too big, so rather than sodium chloride, let's go to magnesium oxide. If we go to magnesium oxide, this is highly favorable, solvated magnesium or hydrated magnesium, and then the oxides. The oxides are going to react with water, but if this were magnesium oxide, the lattice energy is too big and this becomes too endothermic, and it just doesn't happen. It's not going to dissolve. And so things with strong lattice energies don't dissolve. It's too much energy to break apart. So we have some thermodynamic properties. This is after chapter, they switched around the chapters. And so our traditional course covers chapter 13 in Chem 1B. And chapter 13 deals with thermodynamics part 2, where we use a lot of these numbers. And so they already talked about this. Like delta H of formation of H plus aqueous, 1 molar, that's an arbitrary zero. Arbitrary zero because we don't have the absolute zero for that, but we're going to skip this. We're not going to do any thermal calculations.
What's delta G of formation?
Delta G of formation is this. We need one equation that does both of these. We want to minimize and maximize. Sometimes they conflict. And so this is our delta G. So our delta G takes care of both. And therefore we don't have to worry, you know. When does it switch? You know, eventually, okay, maximizing the entropy works up to a certain point, but then the energy is too much. And so if we want to figure it out, then we use delta G. So all the delta G stuff here, all the entropy stuff, entropy, do you know what symbol entropy is given? For energy, we're going to do it at constant pressure, H. For entropy, we use S. G is called the Gibbs free energy. It's too bad. Now we have to switch around everything. Ignore the specific heat stuff and heat capacities. Ooh. Here's some hydrated ions here. These are molecular dynamic simulations. They can make the water start to move here. Okay, if we have something that is not miscible, miscible is infinitely soluble, but most things have a limit. And that limit is called saturation. And so what we have is we have just the pure solvent here, and then over here we have what we call a unsaturated solution. And over here we have a saturated solution. So have you ever tried to see how many sugar cubes would dissolve in a cup of coffee or something like that? Is there a limit? If there's no limit, then we say sugar is miscible in water. You know, how sweet do you want it? You know, if you go to like wherever and they ask you how many sugar cubes you want, you know, you'll say, okay, I'll take 100. Will 100 sugar cubes dissolve in a cup of coffee? No. What is that limit? Well, that limit is saturation. And saturation is going to depend on the temperature. You know, the higher the temperature, the more what we call dissolution. You see the red is dissolution? What do you call the black? What's the reverse of dissolution? We call the black either precipitation or crystallization. And so that would be the reverse. And so over here, the dissolution is much greater than the precipitation. But as you build up more and more ions, then we're going to get the ions to stick on the surface. That would be precipitation here. But eventually you'll get this so saturated that the precipitation rate and the dissolution rate are equal. This is called a dynamic equilibrium. A dynamic equilibrium is it never stops dissolving and it never stops precipitating, but the amounts don't change. And so it's weird, you know, the number of grams of solid and the concentration don't change, but the crystals are always changing. You know? And so if you watch the crystals over time, old ones get dissolved away and new ones form. And so dynamic equilibrium. And it depends on temperature. Most things are more soluble at higher temperatures. This is why I say cold water and then hot water. And so we could see, like KNO3, look at that temperature dependence. You know, at, actually, let's see what the temperature is here. At 0, it's 15. And then at 25, it's up to 40. So we go from 15 grams to 40 grams. This is a huge difference in solubility. And so this is highly temperature dependent. NaCl, just slightly temperature dependent here. So most things go up, you know, albeit at different rates. The solubility goes up. However, take a look at lithium sulfate. What's happening with temperature there? It's going down. So that's an unusual one. That's because most of these are endothermic. Lithium sulfate must be exothermic overall in the delta solution process. So I'm going to cool it. Okay, what we can have is a supersaturated solution, which I didn't talk about here. A supersaturated solution is if nucleation and if nucleation is sluggish. I'll just pick the first one here.
Oh man.
the whole concept of this is, like, some things are much more soluble at high temperature. And so what you do is you heat this up and then you saturate it. And then you cool it down. When you cool it down, it becomes less soluble. But it depends on nucleation. It becomes less soluble and the excess solute should precipitate out. But if nucleation is sluggish, well, what could cause nucleation to be sluggish? Well, one of the things that could cause it is a weird shape. So sodium and acetate is notoriously easy to supersaturate. And the reason is acetate has a weird shape. And so the acetate has to be perfectly aligned with the sodium ions to nucleate a new crystal. The acetates are kind of big floppy anions. And so nucleation is sluggish. You can speed up nucleation by adding C crystals or doing whatever. Let's see how they're going to do it. But what happens is if you slowly cool this, oh, they're going to add a C crystal. I'm going to just turn off the volume here. So they're going to add a seed crystal to help. So this has been cooled down and it's still not precipitating. That's because it's having trouble nucleating. So you can give it a little kick. Let's see if they're going to drop a crystal in there. If they drop a crystal, that serves as a template, and then it can grow easily. Okay, there it goes. Okay, so it looks like they're going to drop a crystal now. Do you see it?
Yes.
Right there. Okay, now that provides a template, and once you have a template, it's easy to grow from there. And so now it's growing, the crystals. But it just had a hard time aligning the acetate perfectly, right? And so this is, if you have like sodium chloride is very hard to supersaturate because
So
it's spherical. There's no alignment problem. It nucleates no problem.
so strange.
Yeah, and so this is all that excess precipitate nucleating out. Here, you can see it there.
So it just becomes a solid again?
Yeah. Yeah, it just becomes a solid again. It's been super saturated. There's too much solute. At this temperature, it was way too much. If you heat this up, you can get all that solid to redissolve. So super saturated. Sodium acetate's the most common one that's demoed.
Wait, we cool it down even further. Can we get an even bigger precipitant?
Yeah, yeah. You can pour it out onto a bench and get it to precipitate. Then you'll see it lots of different things.
So let me just pour it out into my table fast.
Okay, then we have fractional crystallizations. Fractional crystallizations is like distillation. You can crystallize less solute. Let's say you have a mixture. You can crystallize one without crystallizing the other. So this is a mixture of KNO3 and CuSO4. We're not going to talk about fractional crystallization. Fractional crystallization is something you do in Chem 1B a lot. And so skip that. Solubility of gases, we need to know Henry's law. Gases become less soluble with temperature. So as the temperature increases, it becomes less soluble. Henry's law, though, is not temperature. Henry's law is a pressure. And so how much oxygen, how much air dissolves in water depends on the pressure of the air. This is temperature here. And so the higher the pressure, the more gas you're going to get dissolved in there. And so this leads to a potential supersaturated solution. Let's say you have a carbonated drink and it's sealed in here. And so this is sparkling water. Do you know what's in here? Is this air inside here in sparkling water?
No.
No. Do you know what's in here?
CO2.
Pure CO2, or close to pure CO2. And so, do you know how many atmospheres? It's about 1 atmosphere of pure CO2. What happens when you open it? Then air gets in there. And so if you open the bottle, we're going to have air. And so there's going to be a huge difference. If this is pure CO2, what happens is this pure CO2 gets forced into the water. And so that's dissolution. Eventually the CO2 can bubble out, and so that's degassing or whatnot. Sorry, let me turn this on. And so what's going to happen here is this. When you open this, and now this is air, there's barely any CO2 in air. And what we're going to end up with is a supersaturated CO2 because the dissolution's not happening really much anymore. And we're just going to have outgassing. So it's going to go flat. But it's slow because it's hard to nucleate bubbles. And so there are ways you can help nucleate bubbles. You can shake it. Shaking will help nucleate bubbles. Or you can put some salt in here. If you put some salt in here, that'll help nucleate bubbles. That would act as little seeds. And so there are different ways you can nucleate. Or you can put a menthos in here. Menthos has really a lot of surface features that help nucleate bubbles. Or we put boiling chips in here, little crystals with lots of edges, and those edges can help nucleate bubbles. And so Henry's law just says that the concentration of the gas is equal to the Henry's law constant times the pressure. And so here we're going to have a high concentration of CO2. Here we're going to have a low concentration of CO2 because the pressure of CO2 dropped dramatically. You aren't really going to have to do any Henry's law calculations other than know it's proportional. And so this is it. CO2, release that, and it's going to degas. Here's Henry's law in action. The greater the partial pressure, the more you're going to force these gas particles into the water. So this is going to be the highest concentration, lowest concentration, medium concentration here. And this is according to Henry's law. It's going to be directly proportional. And so if this is 4 times the pressure, it's going to be 4 times the concentration than this. This is going to be twice the concentration than this. It's Henry's law. Henry's law, this is one interesting application, the bends. Yeah. You can read about it. I'm going to skip it. All right, I told you we're going to use the mole fraction, right? Yeah. And the mole fraction is here. This is called Raoult's law. Raoult's law deals with colligative properties. And so let me talk about colligative. Colligative means a collection of properties that kind of depend on the same thing. One is vapor pressure lowering. What happens when we have solute in a liquid? It lowers the vapor pressure of that liquid. And so if we have a pure liquid, its vapor pressure is going to be higher than this. We're going to vaporize fewer of the blue when we have solute mixed in there. That is going to be a function of the mole fraction and Raoult's law. So let me go back here. So let's look at the vapor pressure of water, A. We'll call A water. It depends on how many moles of solute we have. And so this would be the mole fraction, is this of A, times its normal vapor pressure, P naught A. If the mole fraction were 100%, this is 100% water, then the mole fraction would be 1 and the vapor pressure would just be the same as its normal vapor pressure. But the mole fraction of water is going to decrease. Let's do an example here. the mole fraction of water will decrease if we add solute to this. And so this is normal vapor pressure we get from the book or the table. And so with here, this is mole fraction of solvent. Mole fraction of solvent decreases with increasing solute. Concentration. So what that does is this. If the vapor pressure is lower, then the most common way this is visualized is by a phase diagram. If we look at the phase diagram for water is interesting because of this curve here. In water, this leg has this positive slope. That means at higher pressures, the solid, is that right? Liquid, gas. This is normal. But for water, it's a little weird. You know what's weird about water?
Is that the line between solid and the liquid goes in a different direction than most other
Yeah,
temperatures?
exactly. For water, this is actually native slope, like this. So this is for water. In other words, liquid phase is favored at high pressures. This is the pressure, this is the temperature. So at high pressures, liquid phase is favored, whereas most substances, at high pressures, the solid phase is favored. Do you see how the line dictates which one's more favored?
Yes.
Okay. And so water is just a bit weird. What happens when we lower the vapor pressure? When the vapor pressure is lowered, the vapor pressure is between the liquid and the gas. And this line here is the vapor pressure line. So when the vapor pressure is lowered, that's going to change some stuff. What it changes is it changes its freezing point and melting point. So if we go to 1 atmosphere here, we'll have the normal melting point, and we'll hit the normal boiling point. So when we transition from a solid to liquid, we call that melting. When we transition from liquid to gas, we call that boiling. That's normal. However, when the vapor pressure is lowered, what happens is it drops this down. And so what we end up with is a melting point that's actually ends up being lower and a boiling point that ends up being higher. This is called melting point depression. And this point here, this is lowered vapor pressure. But raised boiling point. In other words, this is called boiling point elevation. And those are colligative properties. And so colligative property number 2 is melting point depression. Colligative property number 3 is boiling point elevation. The lowering of vapor pressure is going to result in those temperatures changing. Colligative property number 4 is osmotic pressure. Which changes. And so the melting point depression is delta T. Delta T is equal to a constant times the molality. And so it's directly proportional to the molality, the delta T. The delta T here, this is called delta TMP, this is called delta TBP, or delta TB. And this is also equal to a constant times the molality. And the constant's different. So for example, for water, these are different, 0.5 and 1.8 for water. Osmotic pressure is given by pi, and that's equal to the molarity times RT. And this is Raoult's law for that. So I'm almost done here. Thank you. So let's talk about, first let's talk about vapor pressure lowering. One of the big applications of this is distillation. If you have a mixture, actually before I get to the colligative properties, or maybe, no, let me talk about colligative properties first, and then I'll talk about distillation. We'll start off with osmotic pressure. Which one has a higher pressure, which one has a lower pressure? Well, when we add solute in there, probably the easiest way is not to think about pressure, but the easiest way is thinking about equalizing the concentration. So if one side's more concentrated than the other, then they try to equalize. If they try to equalize, we're going to have net migration of solvent over to this side to compensate. And so this is called osmosis. Osmosis happens, like for example, and this is about the extent that you need to know it. How do you make pickles? Do you know how to make pickles?
By pickling cucumbers.
Yeah, you pickle cucumbers by putting cucumbers in brine, and that brine is concentrated, right? And so you pickle, so this would be your cucumber on the bottom, and then on the top would be your brine. And what the brine is doing is it's sucking the water out of the pickle, basically. That's osmosis. Okay, so I talked about isotonic. Do you know why you probably want to use something close to isotonic? Maybe it doesn't have to be exactly isotonic, but it should be close because of this. Let me see if I have this. I don't know if they got rid of that figure. What happens if you explode a cell like a balloon? If you keep blowing up a balloon until it pops, what do you call that for a cell?
Saturation.
Like say I want to blow up a cell and blow it until it breaks the cell membrane, pops. What do you call that?
Saturation.
Well, saturation doesn't necessarily have to pop. Lysis.
Let's break that.
Yeah, in biology, lysis refers to the breakdown of the cell caused by damage to its plasma outer membrane. It can be caused by chemical or physical means, for example, strong detergents or high energy sound waves. Like, you know, in the biochem labs, they're always using the sonicator. The sonicators are those ones that emit high frequency sound. And it's just always screeching. Every day I'd go into the lab and I'd hear the screeching down the hall. Have you heard that? You know, it's ultrasound. They're using ultrasound to break the cells. And it gets kind of annoying after a while, because you hear it all the time. And so what's happening is if you put the cells into deionized water, what's going to happen? Well, the deionized water is going to try to get into the cells because the cells, the intracellular fluid is concentrated. So the deionized water is going into the cell until the cell explodes like a balloon, right? That's lysis. And so you don't want to give yourself an IV of deionized water, most likely, because it could end up leading to potential cell damage. Right? And so you probably want to use like saline or something that's isotonic that has the same concentration. In other words, the same osmotic pressure. Because if it has the same osmotic pressure, then that stuff shouldn't happen. We'll get a nice balance. And so isotonic saline has the same osmotic pressure as blood. However, we call this hypotonic solution. Hypotonic solution is when we're going to have this occur. Yeah. So in an isotonic solution, you just got in and out. It's fine, no problem. In a hypertonic solution, you're going to have pickling of your cells. And so your cells are going to pickle. It's called crenation. Crenation is the pickling of your cells. In a hypotonic solution, you're going to have explosion of your cells, potentially, which is called lysis. And so it depends. If we're dealing with isotonic saline is 0.9% M over V. Hypertonic is what they were talking about. Maybe hypertonic's okay. But they didn't use hyper is no. They were using hypotonic. Yeah, that's right. They weren't using hyper.
Oh, that'd be like 1.1.
Yeah, hyper would be pickling your cells and probably wouldn't be so good. I don't know, or maybe it's good. Maybe further research is needed. So here the cell is stable. Here the cell's been pickled. Here the cell's about to explode. Depending if you use isotonic, hypertonic, or hypotonic. And so that's the biggest application of osmosis. Actually, there's one more big application of osmosis. Do you know what that is? Reverse osmosis. In fact, I just got a new reverse osmosis water purification system.
Osmosis Jones.
I like reverse osmosis. You know, our deionized water is not made by reverse osmosis. Our deionized water is made by resin traps per ion. But reverse osmosis is water wants to flow right to left here. But what you're going to do is you're going to add pressure. How much pressure? Greater than the osmotic pressure. You add pressure here, force the waters backwards. And so you can take salt water and get pure water over here. But the salt water has to drain. That's the effluent, you know. And so you're going to have even saltier water that needs to drain. And so a lot of people say, you know, it's wasting water because you have to flush the salty water out of there. And so you have to waste some water to flush the effluent out. So some people are worried about the waste.
They say waste, but can't the water just be reused once it's been flushed?
No, it goes down the drain usually. It could be reused, but here it is, pressure to make pure water. Now they have hand pumps, you could do this. I have a little reverse osmosis hand pump. It's good. This I prefer, you know, this should filter out any viruses or bacteria out of there too. You know, get drinking water that way. Versus boiling. You know, we used to have to boil water for 5 minutes and kill bacteria, viruses. Or we use chlorine. Did you guys use chlorine?
Pools.
So they used to sell this, like, you know, at the camping stores. You buy chlorine tablets. You buy chlorine tablets, you put those in a water bottle and shake it up. But the water tasted awful.
Or iodine.
Or iodine too. Iodine is good as well.
My
Iodine.
grandparents had a pool. We would buy these like large chlorine tablets, and we would put it in a little bottle, and you'd throw it into the pool.
Yeah. That's another. But I wouldn't drink it though.
Pool water.
osmosis. And then here's the cell. This is nice. This is perfect. This is isotonic. This is what we call what? Hypo or hyper. Hyper.
hyper.
And this would be
Hypo.
hypo. Those are red blood cells.
Are those inside?
Freezing point. There's a hand osmosis system they're using for seawater. Here's the vapor pressure lowering. When the vapor pressure is lowering, it lowers this curve here and this curve here. This is not water. And so that leads to certain applications. You've heard of, what do you put in your radiator? Do you put antifreeze or do you put coolant?
I use ice.
You put coolant. But let's say, you put coolant because we live in Southern California, but let's say you move to Montana or something. Should you drain it and then put antifreeze in there because it gets so cold?
Yes. You should, because different temperatures, different solutions.
Yeah, probably. I mean, if it's like 70 below, like I know people who live in Montana, Wyoming, they have to put heaters on their car. They heat them up before on the engines. But do you know what? They're the same. Antifreeze and coolant are the same. How could they be the same thing?
It elevates the boiling point and it lowers the freezing.
Yes, exactly. Fortunately, you don't have to do anything. Because if you put coolant in Southern California, that's going to work as antifreeze in Montana in the winter. So here, in the summer, it elevates the boiling point. As liquids have much better thermal conductivity than gases, so you want to keep the liquid. And then it also lowers the freezing point, which keeps it from freezing. So you don't want ice in your radiator; it's not going to cool anything. And so a coolant here in antifreeze, same thing. And you need something that's miscible. What's miscible in water? That doesn't corrode the engine. So if you put salt's not very miscible, but that's going to corrode the metal. And so what do you use? You use alcohols. Benzene, probably not benzene because benzene's quite flammable. Alcohols are also flammable, but depends on what proportion you mix. And do you know what the most common alcohol that was used?
Isopropyl.
The most common alcohol, which is miscible in water, is ethylene glycol. I wonder if ethylene glycol has been banned.
Viscous.
You gotta check these things because this is a great alcohol. It's an ethane diol, basically, ethylene glycol. Some of these are quite poisonous, and so it could be banned because people were dumping coolant, like in the sewer drains and that kind of stuff. And so they changed the number of carbons. I think greater than 3 carbons is not, so propylene, yeah. Ethylene glycol has a sweet taste, but it is toxic in high concentrations. This molecule has been observed in outer space. And so I think they changed it to propylene glycol, which is a lot less toxic. Let me just check.
Oh boy, I do love myself a glycol.
Propylene glycol in food, is this additive safe? Propylene glycol is a synthetic food additive
It's tasteless.
and an ingredient in cosmetic and hygiene products.
It's also an ingredient.
However, it has become controversial. This has led to concerns about possible toxic effect. Well, it's probably a lot less toxic than ethylene glycol, and so I think this is one of the substitute antifreeze coolants that they're using. I can't remember. But well, if it's a food additive, yeah. Ethylene glycol is highly toxic to humans and is not used in food products. So propylene glycol is sometimes confused with ethylene glycol, as both have been used in antifreeze due to their low melting points. However, these are not the same substance. It's not due to their it's due to their solubility in water. But it's okay. This is a food law, I think, or health,
This is a food
not
law.
chemistry.
They didn't do their research. They
Yeah,
didn't
they
go
didn't
to
quite
high school
get
chemistry.
the correct reason for that. All right, and so that's the, and so you salt the roads. Why do you salt the roads in the winter?
Because salt will dump ice.
Yeah, salt will lower the freezing point. So Big Bear, lots of salt on the road.
I remember when we used to buy the large Wizard road salts back in Illinois, and you'd have to sprinkle it on your driveway.
Oh, right, yeah. But there's still a lot of black ice.
Oh yeah, black ice is great. It's
And so-
delicious.
The final thing I wanted to talk about is distillation. So let me talk about that, if I can get to stop doing this. If I have a mixture of two liquids, for example, this would be a mixture of toluene and benzene. What's going to happen is if I have a mixture, the more volatile one will vaporize first. And so the more volatile one, which one would be more volatile? So if we have pure toluene, this is the vapor pressure over here. If I have pure benzene, this is the vapor pressure. So pure benzene has a much higher vapor pressure than toluene. And so what this allows me to do is it allows me to separate this mixture based on the benzene. Benzene has a lower boiling point as it's more volatile. And so benzene has a lower boiling point. I'll boil the benzene off first and leave the toluene in solution. That's distillation. And we can understand distillation based on this. What we typically do is something called a fractional distillation. Fractional distillation, these are long columns, and this is used to separate, especially things with a lot of components, and oftentimes with very close boiling points. And so let's say I have, the toluene and the benzene have somewhat close, and so what we do is we look at the liquid here. Let's say I start off with a mixture that has 30% benzene and 70% toluene. So I'd be here. And so in the liquid I have 30% benzene and 70% toluene. However, benzene is more volatile. And so when I vaporize this, I end up with a vapor that contains 50% benzene and 50% toluene. Do you see that? And so what happens is in the liquid, the vapor state becomes enriched in the more volatile one. And then I condense it. When I condense it, I'll have a new liquid. The new liquid is going to be 50-50. And then I vaporize that new liquid and I enrich it in benzene. When I enrich it in benzene over here, now it's going to be 70% benzene, 30%, and then I condense it. And so I make a new liquid here, the new liquid, and then I vaporize it again, and then condense it. Vaporize it again, condense it, vaporize it again, condense it, and then eventually I get pure benzene. This is called fractional distillation. And so that's what's happening in these columns here. In these columns, you're vaporizing it, condensing, vaporizing, condensing, vaporizing, condensing. By the time you're up here, it's pure benzene. We don't have to use a gigantic column like this. In the chemistry lab, we use this. And so we put benzene and toluene here. And the liquid phase is going to have a different composition than the gaseous phase. The gaseous phase is going to be enriched in the more volatile benzene. And then we condense it. This is called a fractioning column, and what happens is it condenses here and drips, and then vaporizes, condenses, drips, vaporizes, condenses, drips, vaporizes, and eventually we end up with pure benzene. And this is called fractional distillation. And we can purify benzene and toluene, no problem. That's an ideal solution. Unfortunately, we have things that are not so ideal here. And so we vaporize it, condense, vaporize it, condense, vaporize it, condense, and eventually we hit this bottom. This bottom is not pure propanol. This is called an azeotropic mixture. And so if I tried to distill propanol in water, I'm not going to be successful. I'm going to stop here. You know, if you try to distill ethanol in water, you know what the max you can get, the max purity? 95%. And so with ethanol in water, you can't get 100% ethanol by distillation. You can only get 95% ethanol. Do you know what they call 95% ethanol?
190 proof.
Yeah, 190 proof, which would be, you could buy 190 proof ethanol? Not anymore? Oh, okay, you can't buy it anymore. I thought they sold it in Nevada, but
Maybe in other states.
in the U.S. and in California, of course, you can't buy it because most everything's, banned in California. But other states you might be able to get it. If you wanted 100% ethanol, you have to do a solvent extraction, and the solvent they often use is like methylene chloride, which is carcinogenic, and so they call it denatured. Don't drink it, ethanol. Okay, the one final thing I need to talk about, actually I was wrong, that wasn't the final thing. There's one final thing I need to talk about. Sorry, I went too long here. Colligative properties depend on the solute concentration. The solute concentration depends. Is it a strong electrolyte, weak electrolyte, or non-electrolyte? If it's a strong electrolyte, you're going to get a lot more concentration. Let's say I had 1 molar sodium chloride. Well, that means you're going to have 1 molar sodium ions and 1 molar chloride ions. And so altogether the solute concentration is going to be 2 molar. And so if I had sodium chloride, I have to double it. If I have lead 2 nitrate, I have to triple it because there are 3 ions per PbNO3 And so we have to look at that for colligative properties. Now what happens is this, we get ion pairing interactions. When we get ion pairing interactions, then it behaves less. And so this is called the activity, or the effective concentration. The effective concentration is going to be less. The more concentrated it is, the more ion pairing. So for example, it should be 2, but it's 181, so that means about 10% of the particles are ion paired at 1 mole. And so this is deviation from ideal behavior. If we have higher charges, it's even larger. So 1 mole PbNO3 it should be 3, but it's actually 131 because we have huge ion pairing interactions because Pb is +2. So we got to worry about ion pairing. And we got to worry about how it splits apart. How it splits apart is I, which is the Van Hoff factor. And we also have to worry about dimerization. Do you guys remember dimerization? Dimerization is when the pairing becomes so strong that it completely pairs. So for example, if you had 1 mole, what was that thing that dimerized quite a lot? Benzoic acid or acetic acid. If you have 1 mole benzoic acid, it's actually half a mole because the ion pairing is so strong, it's all pretty much 100% paired. Here the ion pairing is not so huge. But like benzoic acid, 1 mole is 0.5 because of ion pairing. Or not ion pairing because of the strong dimerization of that. And so these are called effective concentrations or activities. And this is the reason why our pH, pH typically varies from 0 to 14, because below 0, we can't use the regular concentrations. We have to substitute activities or effective concentrations for that. And above 14, we should be using activities or effective concentrations for that as well. So between 0 and 14, you can do your normal pH calculations. But at the extremes, we got to modify it a bit to compensate for the high concentrations. High concentrations being more than 0.1. Oh wow. Okay, sorry. Went too long. You can take a break, and then what we're going to do is we're going to do a quick. We're going to do a quick lab